In the last video, we did a calculation where we took some experimental data that was collected on a reaction between an acid and a base, and we figured out how much heat was produced by the reaction or released by the reaction. Here was our final answer. And at the very end of this calculation, we posed this question: is this the best way to talk about how much heat this reaction produces? It might not be, because if we vary the amounts of acid and base that we've got, we're going to change the amount of heat that the reaction releases. Just like if you're burning a fire, if you throw 10 logs on the fire, you're going to produce a lot more heat than if you threw 1 log on the fire. Is there some better way to report that? You can talk about how much energy that you're releasing per log burned, or per pound of wood, or something like that. And we're going to do something similar to that. We could talk about how much energy this reaction is producing per mole of limiting reactant. For a reaction, it's the heat absorbed or released by a reaction per mole of limiting reactant. Now, if we take a look at the experiment that we did here, we have a 1-to-1 mole ratio between these things, and we're adding equal volumes and equal concentrations of these things. So in this case, we don't have to worry about which one of these two things is the limiting reactant. If I can pick either one and it's going to work. If I want to write an equation for this statement that I've just made, it looks like this. We're going to call the reaction enthalpy delta H. It's a change in enthalpy. It's the enthalpy of the products minus the enthalpy of the reactants. We'll look at that more in the next worksheet, actually. It's equal to the Q reaction that we just calculated over moles of limiting reactant. In the calculation we just did, we said that this was minus 1422.5 before we rounded it off joules. The minus sign there is going to be pretty important. Don't lose it. Now we got to figure out how many moles of limiting reactant we've got. Now it turns out to be pretty easy. We could figure out how many moles of this we had, how many moles of that we had, and turn them into a product and see which one was less. They're both going to be the same, actually, though. So we can take, like, let's say the 50 milliliters of HCl solution, turn it into liters. 1 milliliter is 10 to the minus 3 liters. And then use the concentration, the molarity of that, to turn liters into moles. It said it was 0.100 moles of HCl per 1 liter. So now you can see how the units go. Milliliters cancels milliliters, liters cancels liters, and I'm left with moles. And that will give me the number that I put on the bottom there. So it's going to be 50 times 10 to the minus 3. That's like bumping the decimal place over 1, 2, 3 places. So far I have 0.050 liters, right? Times this, So that'll bump the decimal place over one more place, and that'll be 0.0050. Let me see, here I should have kept that like that, because I have 3 significant figures. So that's how many moles of limiting reactant I've got. Now what did I do again here? I took the volume of solution times the concentration to get moles. And if the volume was given to me in milliliters, I have to turn it into liters first. So that's all I had to do. So our delta H, our reaction enthalpy for this, is going to be minus 1422.5 joules divided by 0.00500 moles. And what's that going to be? Let's figure out the number. Okay, so I get a big number there, see? It's going to be, let me see. Let's double check that and make sure that I typed it in right. Okay, it really was that. It's a big number. I had to do kind of a double take on that because I'm putting in just numbers I made up into this problem for the temperature rise and whatnot, so I'm getting something I don't quite expect. All right, how many significant digits? Well, this has 3, so this is only going to have 3. So really I need to round that off. Now, that's a big number, so usually people don't write the reaction enthalpies in terms of joules per mole. They'll do it in terms of kilojoules per mole. There are 10 to the 3 joules in 1 kilojoule. So if you divide that by 1,000, you get. Now, very often in your problems on your worksheet, they're going to ask you for a delta H, and they're going to want it in kilojoules rather than joules. All right, so I defined a reaction enthalpy, and I justified it a little bit. I said this is a measure of how much heat the reaction absorbs or releases per mole. I put it on a per mole basis. But what is enthalpy actually? We'll look at that in the next video.